So I'm going to talk about a foundry in a box. Sometimes we call it printing, sometimes we call it additive manufacturing, but it's an entirely new technology. A lot of you are familiar with inkjet, screen printing, aerosol jet, and so forth. This is very, very different. So I'm going to first give you an introduction, what the technology is, and then talk about the technology itself, which is what we call directed assembly. That means taking the particles from a liquid and directing them to exactly where you need them. And we have about 4 different applications of directed assembly. I'm going to talk about 2 of them, and then I'm going to talk about what kind of printing do you get. We get crystalline and polycrystalline structures, amorphous structures, and then I'm going to talk about the applications, advanced packaging. A lot of it is advanced packaging, printing of capacitors, transistors, diodes, and so forth. And then I'm going to show you the fully automated equipment that will do this. So what if you can have your chip or advanced package done in 1 day on the same machine at about 100 times less cost than typical fabrication and at a 25 times smaller carbon footprint? This is compared to foundries. Okay, and yes, this all can be done with this new technology. And this new technology was developed over the last 10 years or so, more like 14 years actually, and funding from the US government, agencies and companies and so forth. So right now we have actually, this is Gen 2. We have Gen 3 now that is built in. There's a robot there that handles the substrate. So basically the feature size, we demonstrate the technology to go down to 20 nanometers. It's about 10 to 100 times reduction in fabrication compared to conventional semiconductor manufacturing. It's about 10 to 100 times faster throughput. It's about 1,000 times reduction in materials. And of course, their steps are, the number of steps is reduced dramatically because you're doing everything using pretty much one process on one tool. And it's about 1,000 times faster than inkjet or 3D printing. It can print crystalline metal and semiconductor. And so to make clear that we don't use etching, we do not use vacuum deposition, and a lot of the processes are room temperature, and there's no chemical reaction, and it's all done in liquid. And in concept, anything you can suspend in a liquid in terms of nanoparticles, you can actually print. So you're not limited to the typical materials that you have today. So how does it work? So this is one of the techniques where you put the, first of all, we use lithography. So our equipment comes with lithography integrated. So all you need is just the supplies, your design files, and your substrate. That's all you need. And everything is included in the equipment. And so this is one example where you actually, the lithography is done here. These features could be done in a printed, let's say, dielectric, like silicon dioxide or alumina or hafnium dioxide. And basically and there would be a conductor at the bottom, like a interconnect, for example. And then you have a counter electrode in a bath. And then you assemble. This particular one is gold. And when you do this, the process takes about 1 minute for a 4-inch substrate. And then at the end, you get actually a complete structure. In this case, if the particle is small enough, you don't even need sintering. It's centered in situ. And so you can see here, you see copper, aluminum, polymers, silver, and so forth. So the question is, since there's not even centering, what happens inside? Are there voids inside, for example, like you see in some of the printed structures? What kind of structure do you get? Do you get amorphous? Do you get polycrystalline? And what kind of conductivity do you get? And so we answer these questions. First of all, we can do, for example, these are pretty small. You can go to a microscale or you can go to nanoscale. You can go even as small as 25 nanometers. So if you take a cross-section of these pillars, for example, you can see that there are no voids. It's actually polycrystalline. There's 2 crystalline structures with 1 grain boundary. And here you compare the resistance of nanoparticle-based pillar and electroplated pillar, and you can see they're